Hello everyone, this is Faisal Akawi. Welcome to the network and the transport layer. We will spend 2 weeks on those two topics. There will be a total of 6 recordings. One recording, I will discuss the transport layer protocols and functionality. Second recording, we will talk about the network layer protocols and functionalities. We will talk about routing protocols in one recordings. We will talk about an TCP IP example in one recording, IP addressing and subnetting in one recording. There will be a recording about NAT and PAT. So to begin the discussion, it is worth noting that the top 2 layers within the 5-layer model, the application layer and the transport layer, are the software component. This is our software that exists on the machine itself, both of these 2 components, where the network layer, data link layer, and the physical layer are considered to be a hardware layers. This is things you could really buy and touch and connect and configure, as you have seen in the packet tracer. We will focus our attention to the transport layer in this recording, as it acts as the middleman between the application layer and the network layer. It is responsible, the transport layer is responsible of connecting the application layer down to the network layer. The transport layer has many functionalities, such as it takes the message from the application layer, it chops it into pieces, it numbers it, it reassembles the message on the other end, as we will go in detail and discuss them. I will also open the TCP protocol and look at the overhead that the transport layer adds to each packet comes down from the application layer, and map the protocol, the TCP protocol components, to the functionality that the transport layer provides. The network layer functionality will be addressed in a separate recording, but it is mainly to transmit the piece of data or the packet from one point, from one machine to another. For example, if I want to take a drive from Chicago to California, there could be multiple paths that I could take. And that's sort of the network layer. The network layer determines which path the packet needs to take to get from point A to point B. Let's begin the discussion by taking a look at the TCP protocol that exists at the transport layer. Keep in mind that while we are discussing the transport layer, the TCP is the most common protocol that exists at the transport layer. There are other protocols that exist at the transport layer. Feel free to read about them or Google them if you wish, but the TCP is the most common protocol that's being used today at the transport layer. The transport layer adds anywhere between 20 to 24 bytes overhead. So when the message comes from the application layer to the transport layer first, it will segment it into pieces if it is more than 1500 bytes. And the transport layer will add the overhead that you see down here to each packet. So when you compute the efficiency for transmission later on, you need to keep in mind that this overhead, which is about 24 bytes, it's being added to every segment at the transport layer. The first 2 pieces of information determines the source and the destination port number. As you will see shortly, the transport layer, let me clear the screen first. The transport layer serves the application layer. We are used to opening more than one application at the same time. So I could be having my email open, I could have my IE open, I could have Firefox open, I could have multiple applications open at the same time. But think of it this way, there is only one transport layer serving that information. So each application will have a specific port number, and that what we will be sitting in the first two sets of the overhead that the transport layer adds. This is the overhead that the TCP adds. It will keep track of the source port and the destination port. In another slide or two, we will have quite few examples. We will have also the segment number. As we know, one of the major responsibility of the transport layer, if you are sending me an image, and if the image 1 megabyte in size, I cannot, as a transport layer, cannot send that 1 megabyte as one piece. I have to take it and I have to segment it into pieces. And one of the responsibility of the transport layer to say this is piece 1, this is the second, this is the third, this is the fourth, and so forth, so on. So this particular piece of information sequence number, it determines which piece, which number of segment I am working with, and that is used on the other end, because if you take that 1 meg and chop it, let's say, into 4 pieces or 5, so you get this is 1, 2, 3, 4, 5, and you transmit it to the other side, they might get into the order of 1, 5, 4, 3, and 2. This is how I might receive them. The transport layer on the receiving end will say, okay, this is the first piece, second, third, fourth, and fifth, and it will reorder them. Transport layer also has the acknowledgement, as we will see shortly. It's a connection oriented. The transport layer on one machine has to open a communication, just like me calling you. I have to ring your phone. I have to say hello. You would say hello back, and then we would start the conversation. This is how the transport layer through the acknowledgement, which is about 32 bits of information exchanged between the sender and the receiver to acknowledge or disacknowledge the message. So this is what we refer to as the ACK, A-C-K. That means when I say ACK with a sequence number, that means I did receive that message that you labeled 5. Or I would send a NAK indicating that I did not receive the message and you need to retransmit. There is also here a flow control. This is what we call the window size. Let me clear the screen. The flow control is PC1 or the transport layer on PC1 will negotiate with the transport layer on PC2 after they establish the communication. How many packets can I send? So we call that the sliding window. So let's say the window is 1, 2, 3, 4, 5. PC1 and PC2 agrees on the sliding window to be 5. So PC1 will send 1, 2, 3, 4, 5, and then it will wait for an acknowledgement for all 5 packets. If it receives the acknowledgement for all 5 packets, then it will send 6, 7, 8, 9, and 10, and etc. and so forth. This is flow control is negotiated between the sender and the receiver. There is also, if you remember from the Ethernet, when we open Ethernet also has a flow control as a part of the Ethernet protocol. So if you look at the 5-layer model, the transport layer will agree on the window size of 5. But if after start transmitting, the Ethernet gets over flooded, the Ethernet flow control will override the transport flow control at that time. So in other words, you and I at the transport layer, TCP, we both agree that the window size is 5 through that flow control. We start transmitting, then we find out that the Ethernet also has a flow control. So once we start transmitting the 5 packet, after 5 minutes, we determine the Ethernet determines that on PC2 that it's being overflooded. It will use the flow control in the Ethernet to override the flow control in the transport layer. There is the CRC16. We know what that is. This is a mechanism for the sender and the receiver to check whether there is an error in the message or not. You will see that this exists in the transport layer. It also exists in the IP protocol and the network layer. It also exists at the Ethernet protocol at layer 2. So it exists at layer 4, it exists at layer 3, it exists in the protocol at layer 2. We do not do error check at the transport layer or at the IP protocol. We do it at the Ethernet. So if layer 2 determined that there is a problem with the packet because of its CRC16, the Ethernet will do what with the message? The Ethernet will disregard the message. It will destroy it if there is an error in it. And the transport layer, through the acknowledgement, will say, okay, I did not receive packet 5 that Ethernet destroyed. It will send a NAC and it will get a second copy. Keep in mind that this is true in a local area network where it is a lot cheaper for me to ask for a second copy of the frame rather than me trying to correct the frame. If the message were to be sent from the Houston headquarters to the Mars Pathfinder outside the space where it takes 20 minutes round trip, and if there is the Mars Pathfinder or the software, the transport layer at the Mars Pathfinder find out there is an error in the message, in that case, it's a lot easier or cheaper to attempt to correct the message rather than try to ask for a second copy. And there are algorithms to correct the message based on the message that it has been received. Let me take a second and clear the screen. All right, some reason I cannot clear the screen, but fine. Let's move on to the urgent component. The urgent component, or the part of the overhead, this is where you could give frames different priorities. This is how the TCP gives you quality assurances. So if you are using voice over IP on the same network, the packets that are labeled with voice, they tend to have a higher priority than the packet with data. So if we're talking and using the voice over IP on the same network, and we're talking and we're sending data, it's okay if I send a packet 5 of my email 2 seconds later because it will sit and wait for me. But if we're using the phone system, I cannot receive packet 5 before packet 3. So the transport layer will distinguish between the voice packet versus the data packet. It will give the voice packet a higher priority over the data packet. So if these packets or frames arrive to the router will give the higher priority, the first write to be moved on the network over the data. There's about 32 bytes called optional. They are used sometimes, but they are not. And that's also possess some security issues. As you will see later, hackers will use this through what we call covert channels to smuggle some data out through the unused space. You'll see that in the security courses, and there is the actual data. That's the actually why we have 20 to 24 bytes of overhead. So if this 32 bits are not used, that will reduce the overhead. For the sake of efficiency, I will always give you the overhead size, which is I will always use 24 bytes of overhead when we use the TCP protocol. Another major protocol used at the transport layer is the UDP. UDP is connectionless. Connectionless meaning that I don't have to establish a connection just like the TCP. Your TV uses UDP. If I'm using a TCP to send you an email, the TCP will establish the communication. I will send you the email. I'll receive a confirmation that you received it, and then I shut off the communication between the sender and the receiver. If you did not receive a packet, I will resend it to you, or a frame. In case of UDP, your TV, so if you're sitting watching a movie and lightning happening and for some reason you missed a few frames, the TV station is not going to know about it, number one. And it doesn't make sense to retransmit the frames 5 minutes later. So if you're watching a movie and 5 minutes later you get few frames that you should have seen 5 minutes before, it doesn't make sense. So UDP, what we call a connection list, there is no confirmation. The sender just sends the data and assumes that the receiver have received it. Your radio station works that way. DHCP work that way, uses UDP packets. But those are the two most common protocols used at the transport layer today. I will have a separate recording about the network layer protocols and functionality, but mainly today we have IPv4 version 4 and we have IPv version 6. We have that many IP addresses of IPv4, and we have that many IPv addresses of version 6. Technically, in the field, we say that we have unlimited number of IPv6 because we have so many of them that we will never run out of IPv6. But I'll have a separate recording about IPv4, what it is made out of, and how to subnet it into more than one segment. This is sample of the IPv4 protocol. As you'll see, the first 4 bits contains the version, which tells you whether it's IPv4 or IPv6. There is the total length of the packet, which tells you the beginning and the end. There is the hop limit. Hop limit means if I have routers connected to each other's and I'm sending the message from LAN 1 to LAN 2, my frame will leave, and there is the hop limit. Let's say I mark the hop limit to be 5. Once it gets to the first router will decrement the 5 into 4. This router will decrement it to 3. This guy will decrement it into 2. This guy will decrement it into 1. And if for some reason, let's say there's a router here, it decrement the 1 to a 0, this particular router will not forward the packet onto anywhere. It will just simply destroy it once the hop limit reaches a 0. We use that to make sure that a frame does not stay on the network indefinitely. So if LAN 1 sends a message to LAN 2 and it does not receives it within 5 hops, then the last router will sort of drain the message out. We'll take it off of the network. This way, the packet does not continue to overflood the network. There is the CRC 16 that I mentioned a bit ago, where it also exists. Error detection can happen at the IP, but we really don't do that at the IP. We do it at the Ethernet. So each one of these router has an Ethernet. Once the message goes in, the Ethernet, which is the protocol that exists at layer 2, will check if there is an error. If there is an error, the router does not need, if there is or is not, the Ethernet will deal with it. Therefore, the router, which is the IP protocol that exists at the router, does not need to do it. So while the IP address has the capability of doing error detection, it's not done at the routing level, but it is part of the protocol and it's part of the overhead and it exists. There is the source and the address, source and destination address. In a future recording, I will talk about 3 different addressing that happen when you go through the 5-layer model. When you go from the top to the bottom, there are 3 different addresses that you need to be aware of. So when we say source and destination address, you have to know where you are within the 5-layer model. So since I am talking about the IP, the source and destination address will contain an IP-like address such as 192.168.5.1. But if I'm talking about the source destination at the Ethernet, there you expect to see an A1, C1, an address type like for Ethernet, a physical address. If I'm talking about the source and destination address at the transport layer, I'm expecting to see www.northwestern.edu, that type of an address. So when we say source destination address, you have to be aware where you are within the 5-layer model, and that's sort of crucial to know what source and destination address exists. There is, of course, another 32 bits optional. It also exists at the IP, in the IP protocol overhead. Sometimes it's used, sometimes it's not, but that's where the overhead that will be added by the IP protocol. I meant to say IP protocol. Here is a quick peek at the IPv6 protocol. Same information for the vast majority, the hop limit. Notice that the CRC 16 was removed from IPv6 since we do not need to do the error checking at the network layer. Also notice that the optional header still there, that's part of the whole framing. The overhead is about 40 bytes, where in IPv4 the overhead is about 24. So the IPv6 adds a bit more overhead than the IPv4, but I will discuss the difference between the two in future recordings. The next few slides has somewhat redundant information, which talks about the transport layer functionality. There could be multiple protocols at the application layer. Here are sample of the protocols that exist at the application layer, which is the HTTP, which again, the purpose of it is to transmit to transmit web pages from one server to a client and vice versa. We know that HTTP is not as secure. The HTTPS, which is a secure connection, your banking system will not allow you to connect to it unless you are using HTTPS. Notice that the port number that will be used, FTP uses port 20 and 21. SMTP, which is a protocol at the application layer, we use it to send emails, uses 25. IMAP and POP are two protocols to receive information to receive data and manage emails on the servers, uses 143 and 110. You don't need to memorize these port numbers. I'll never ask you to do so, but these are sample of them. The next slide gives you a clear indication of the functionality how the transport layer may serve more than one protocol at the application layer. So take a look at this picture or this image. So you have your client. Your client can access a web server, a second server, or two different servers at two different locations. So I, as a client, so my transport layer right now, which is my TCP, is serving more than one application protocol at the application layer. So the client is opening the browser, the Internet Explorer browser, browsing the internet. It's checking its email, so it's probably connecting to an SMTP server through the email, and it's downloading your real player and probably playing music by browsing that music. And so it could be accessing more than one application at the same location or different locations. So the transport layer, when we say it serves the application through the port number, the transport layer, when the message comes, it has an IP address, has a source and destination port, and that's how the transport layer, whether it's on the sending or the receiving, keeps a track where the message is coming or going. In a separate recording, I will open an entire TCP example and how the message is formulated from the client and what it contains going to the server and it's coming back from the server. But for now, one of the main responsibilities of the application layer is simply, the transport layer is simply to serve the application layer and keep the information coming down from the application into the network. And when the message comes back from the network, the transport layer needs to know to what window or to what protocol to send that message. And that's easily done through the port that it is done. Every application protocol and the application layer has a port, a specific port that it needs to deal with. If you were to develop your own application, let's call it application X, you would contact this organization, and an organization will say, okay, we're going to give you port 1229. They're going to give you a port that's not being used. You publicize that to the world that you developed application X, and anybody want to use application X, they have to have that specific port open. Another major responsibility of the transport layer is simply to segment the message, as we've seen in the past. If the message at the application layer comes as too large, if it is greater than, by the time the message hits the physical layer, it has to be a 1500 bytes long. So if I have a 2000 bytes message, the transport layer needs to segment this message into two segments. Maybe it will say, here's 1000 byte and here's another 1000 bytes, and then it will that's the responsibility of the segment of the transport layer, is to segment, to take that message and chop it into pieces. Now the transport layer knows, well, it says, okay, I have the HTTP, it adds about 100 bytes, the TCP adds about 24, the IP adds 24, the Ethernet adds about 34. So the transport layer will say, okay, while the PowerPoint says 20 and 20, but it could be anywhere between 20 and 24. The transport layer says, I know that the TCP will do 20, and the IP will add 20, and then there is another 34 for the Ethernet. So it will adjust the size of the packet. So you take that, you subtract 34, and that will give you the actual segment size where it is. So by the time the message hits the line, it has to be 1500 bytes long, including the data. So whatever the data is, so let's say the red is the data, plus the 100, plus the 24, plus 24, plus 24, it has to be a maximum of 1500. So that's what the responsibilities of the transport layer is, segmenting the message into smaller pieces. And in previous recording, we highlighted why the 1500, why not 10,000, right? Remember, the bigger the message, because the efficiency is the data divided by the data plus the overhead. Now, the bigger the data, the better the efficiency. So if you go to 1500, we figure the efficiency probably anywhere 98 percentile. If we go to 10,000 for the piece of data, you know, the efficiency goes up much higher, so 99 point something. And we determined back then why is the 1500 is the magical number. If you don't know why, please go back and view the Ethernet protocol. To illustrate the point one more time, the message comes in, let's say it's 2000 bytes. The message will cut it into 1000, 1000. It doesn't have to be, by the way. It could be any value as long as within the range. TCP will add 24, 24. The IP will add another 24. And the Ethernet will add 34, 34. Now, the only tricky part here is that the part of the message up here, it has the 100 byte of HTTP. Notice that the transport layer will add the overhead to each segment. The network layer will add the overhead to each segment. Ethernet will add the overhead to each frame. But the HTTP, which is 100, will only be added once to that first segment. Because I don't need HTTP in the second one, because when it gets to the other end, it only needs the HTTP once. So the efficiency, it's usually, in this case, it's this. It is the data. So let's say the data is 2000 divided by the data, which is 2000, plus the overhead. What is the overhead? The overhead is 100 plus 2 times 24 plus 24 plus 34, whatever that is. So the transport layer, TCP, will be added twice. The IP will be added twice. The Ethernet will be added twice, but the HTTP will only be added once. And because of this session management, or the type of the session management, we call this a reliable end-to-end connection TCP. None of this happened in a UDP. In a UDP, TV transmits all the time. Once you open your TV, you start receiving the packets on the line. That's all about the transport layer. Just to summarize it, transport layer establishes communication between PC1, PC2. It segments the message. It reassembles the message on the other end. It agrees on the packet size. While it's 1500 is the max, sometimes it might renegotiate it down. In today's technology, the 1500 can be extended, but I'm not going to go through why is that and when, but keep in mind that it could also happen. The TCP will serve many of the application protocols that exist at the application layer. So that's why we say the transport layer connect the application layer with the network. So it sort of acts like the middleman between the application and the network layer. That is all what I have for you about the transport layer. I hope you find this informative, and we'll see you in the next recording.